Whenever I say that I'm a cryptographer, people come to me and saying that they discovered an unbreakable cipher. But of course, whenever I listen to them, I realize that the cipher they designed can easily be broken, can be easily broken. So it is not that easy to design an unbreakable cipher. But also, whenever I give a talk about cryptography, people ask me if it is possible to design an unbreakable cipher. And the answer is yes. Actually, there is an unbreakable cipher, which is called one-time pad or Vernam Cipher, which is actually famous and used a lot in the history. But before seeing it, you might think that if there is an unbreakable cipher, why we are not using it? The answer is simple: it is not practical. So let's see what this unbreakable cipher is, and then see how the Steam cipher is trying to have the idea behind this unbreakable cipher. So one-time pad works like this. We generate a very long sequence of random bits, and this is called one-time pad. Whenever you have the plain text, you XOR your plain text, so you turn your plain text into zeros and ones, and you XOR it with this long random sequence and obtain the ciphertext. So the person you want to communicate also have this random sequence of bits. So they XOR it with the ciphertext they receive and obtain the plain text back. So if you don't know what the XOR operation is, let me give you an example like this. So you turn your plain text into zeros and ones. So you randomly generated zeros and ones as your one-time pad, and you gave this one-time pad to the person you want to communicate in a secure way somehow. So this way you can communicate. So what you do is just perform an XOR operation. XOR, which is exclusive OR operation, is simply addition in modulo 2. So it is like normal addition. So 1 plus 0 gives you 1, or 0 plus 1 gives you 1, and 0, 0 gives you 0. But the only exception is that 1 plus 1 results in 0, since we are working in modulo 2, but also we don't have a carry bit here. So the additions are actually bitwise. They don't affect any previous or following bits. And one-time pad must be truly random. So if it is not truly random, then the cipher can be broken. And also another problem is that you have to use every one-time pad only once. If you use it twice, when you use it twice, the cipher is broken, can be easily broken, sorry. So this is why it is impractical, because, for instance, if you want to send like 1,000 WhatsApp messages to your friend, you cannot beforehand give them 1,000 one-time pads so that they can XOR and obtain the message. So this is why we don't use it in practice. But it provides perfect secrecy. Ciphertext provides no information about the plaintext. The one-time pad usually printed on a single page with very small letters. This is why it has the name one-time pad. And instead of working bits, one can work on letters or characters. So this is why before the invention of computers or cipher machines, people used this algorithm on letters. Idea of one-time pad leads to the idea of stream ciphers. And we will see in a minute how. And again, the problems for the unbreakable cipher was where key is too long, key distribution is a problem, and randomness is also a problem. You have to generate the keys in a random way. So Vernam Cipher, which is also called one-time pad, uses a long stream of key consisting of random bits. The length of the key is same as the message and used only once. Encryption is just combining key and the plaintext bit by bit. Shannon proved that one-time pad is unbreakable. So guessing the key is equivalent to guessing the plaintext actually. Because of requiring a vast amount of key information, one-time pad is impractical. But a synchronous stream cipher attempts to capture the spirit of one-time pad by using a short key that generates the key string which appears to be random. So this time, instead of truly generating a truly random key stream, you are actually choosing a random key which is short, like 16 bytes, but using that key and some algorithms, you generate a key stream, very long key stream, which appears to be random. Such a key stream is called pseudo-random, since it is no longer random. And much of the work in the field of stream ciphers is deciding what constitutes a pseudo-random sequence. In this context, key stream generator stream ciphers are evaluated by means of quality of the key stream it produces. And a key stream generator stream cipher is as secure as its output is closer to be random. So this is the main idea behind the security. This concept can be understood in two ways. Is there some imbalance to the way the sequence is generated that allows the cryptanalyst to guess the next bit with some probability better than that of random guessing? So this is related to the appearance of the key stream. And second is it hard to reproduce the sequence? So this is related with the inherent complexity of the sequence. For this reason, with these two approaches, we have the following ways of measuring the quality of the key stream. For the measures of the appearance, period and statistical measures are used. So period should be large, as we already talked before. And there are many statistical randomness tests that can check when if a given sequence is random looking or not. And for the complexity approach, there are some methods like linear complexity, max order complexity, or Lampard-Ziv complexity, which actually gives you some value whether the complexity is high or not. So this way we can measure the quality of the key stream. So these are actually what is done in the area of stream cipher cryptanalysis and so on. In the design also we try to use those approaches to design something good. So stream ciphers were faster than block ciphers. So most of the block stream ciphers I'm going to talk about here are a lot faster than DES or AES. But until after the lightweight designs, after lightweight block ciphers are designed, it turned out that block ciphers are somewhat faster or require less area than stream ciphers. This is mostly due to the internal state, because we are trying new designs try to have huge internal state, which already requires a lot of gates in the hardware. So for this reason, old standards in communication are all stream ciphers, like as you can see here, GSM standard A51 or wired equivalent privacy, which is used in wireless communication, is RC4 in our earlier Wi-Fi standard, and in Bluetooth we have E0. But again, as I told you, after the lightweight designs of block ciphers, now in 3G we have A53 standard for GSM communication, which is a block cipher called actually Kasumi. And in the VPA or VPA2, we can use AES, which is also a block cipher. So we kind of moved from stream ciphers to block ciphers. But in a few years ago, Salsa or also Cha-Cha became important in TLS, so we will talk about it at the end. Moreover, there was a competition called Eastdream. Eastdream competition started in 2004 and had 34 candidate algorithms, and 7 of them are included in the final portfolio in 2008. So this competition was not designed by NIST, unlike most of the competitions. This was designed started by academicians, because these competitions actually increases our knowledge in a specific area, and we realized that we don't have much ways of analyzing stream ciphers. For this reason, this competition was started in 2004 and ended in 2008. These 7 algorithms that are included in the final portfolio are divided into 2 categories. One of them is hardware. So Grain, Mickey, and Trivium were in the final portfolio for the hardware case. And for the software, HC128, Rabbit, Salsa, and Sosamonic was in the final portfolio of this competition. And from this list, Trivium became ISO standard in 2012. And Salsa, it has a modified version called Cha-Cha, is also now included in TLS 1.3. So those are the actually stream ciphers that we use most of the time in daily life. except E0 if you are using Bluetooth, and if you are using a very old protocol for your Wi-Fi communication, then you might be using RC4, which means that anybody can capture your Wi-Fi password, which will be talked in the following slides. So let's see what are the current standards. So NIST doesn't have any stream cipher standard, but it has some block cipher mode of operations like counter mode, which actually turns a block cipher into a stream cipher. So probably for this reason, they didn't choose any other stream cipher standards. But ISO has some standards. So in this following standard, 18033, which was last update in 2011, describes both pseudo-random number generators for producing key stream. So these are the stream ciphers that are going to produce key stream, but also output functions to combine a key stream with the plain text. So I told you that the basic way of combining the plain text with the key stream is just XORing them. So in ISO standards, this is referred to as binary additive output function. So you can use it like that, or you can use some different construction called multi-S01 output function for the combining key stream with the plain text. But for the stream ciphers, which can be used for producing key stream, the following 5 are ISO standards. They are Mugi, Snow 2.0, Rabbit, Decim version 2, and K-Cipher 2, which is also known as K2. So these are the ISO standards, which can be used in many applications. But also we have some lightweight stream cipher standards by ISO. This is last updated in 2012. It specifies 2 dedicated key stream generators for lightweight stream ciphers. First one is an Ekoro. It supports 2 key sizes, 80-bit and 128 bits. And second one is Trivium, which supports 80-bit key, but the key is really short here. But as far as I know, recently some attacks are applied to the full Trivium, which appeared in ePrint, but hasn't been published yet, as far as I know. So without a peer review process, we cannot say that it is broken or not. But regardless, 80-bit key is short for this for 2021 actually.